Hello everyone and welcome back to NL 582 Modeling and Control of Electric Machines and Drives. We're still talking about DC machines. So we started talking about a very simple machine and starting building up on this until we landed out by the end of the last lecture to a complete typical DC machine that you can see in some industrial facilities. You may see them after this, but the idea is just we have consistently talking about those basic principles we need to have in mind to build on them while we're talking about DC machines or any kind of machine we'll be talking about after this. So in general, what we talked about last time, let me write this down to make it more clear. So we have investigated how to solve the problem of having switched direction of the induced, or let me say it, generated, they are the same meaning about this, or give the same idea, voltage of a DC generator, or the torque developed by a DC motor. So we had before that we have a problem. It's just our machine does not have unidirectional voltage induced or a torque, and that was a problem in terms of a DC machine when we're talking about a generator. For a DC generator, we wanted the output to be just DC. Okay, so that was the voltage induced in any coil side. Okay, and if you remember, it was having the shape like this. It has sometimes positive, sometimes negative, and sometimes zero. And we turned this, the last lecture, into something like this. That was the E of a coil side, or also the torque generated by a coil side, whatever it is you're talking about. If it is a generator, we're talking about the E and the coil side. If it is a motor, we're talking about a torque. So this, we had just make it like that. It's all the time positive or all the time negative, whatever it is, but it's unidirectional. That's what we called DC commutation. We have done this by the use of two valuable assets, the split ring commutator, or what we call it a commutator for briefing, and brushes. Okay, so by using the split ring commutator and brushes, they're actually doing the exact same job of modern days power electronics. Okay, so nowadays we have what we call a power electronic DC to AC converter. Okay, we call it a rectifier, and that is used power electronics to transform from AC voltage to a DC voltage. Okay, and that's what actually this commutator and brushes do in a DC generator. At the same time, we have nowadays what we call a DC to AC inverter made by power electronics, and we'll be talking about this when you're talking about the control of induction machines later in the course. So the modern day power electronic DC to AC inverter does the same job like the commutator and the brushes do in a DC motor, because it's taken the outside DC voltage applied to the motor and just inside it's just make it a positive and negative to make this torque happens and make the torque unidirectional. So here's the idea of using a split ring commutator and brushes. Okay, back in the days when they didn't have these power electronic converters, they just used this, which has a mechanical feature. It's a mechanical device that can do the same job as modern day power electronics. Okay guys, So that was how to solve this bidirectional problem and just make the voltage and the torque unidirectional. Okay, but the problem of these zero periods we didn't solve. So solving these zero periods, we have done this by using higher number of coils in the rotor. Okay, and higher actually, yeah, so just using higher number of coils and the rotor actually solved this problem for us now, if you remember this. And we also talked about increasing, so this using higher number of coils and the rotor solves the problem of zero voltage from a generator or torque from a motor. Okay, and actually we even added, we just talked about that we can add more poles to the stator, and that will increase the generated voltage of a generator or the torque developed by a motor. Okay guys, so the basic idea is just we are now having a complete DC machine. Okay, what this complete DC machine looks like, it will look like something like this. Let me grab you a photo, will be more convenient. Yeah, something like this. Again, this photo is taken from the same video we've been talking about last time. It's from learnengineering.org. You can see this full one. Let me just grab it here. Yeah, okay, so if we're talking about this, so I know it's a little bit confusing, but let's just try to look at it. So here is your rotor that's inside here. Okay guys, so these inside cylinder are the rotor, so that's basically those are your rotor coils you're seeing here. Okay, and we talked about this last time, that rather than just having one coil, we have now multiple coils to solve our zero problem. And also the more coils you have, the more voltage generated, if you're talking about it's a generator, or the more torque you have from a motor. Okay guys, and this set, it's the thing we're talking about, that the split ring commutator, and here is your brush. Okay, so this is the brush, and there's another brush down here, so those are the brushes, and this is the commutator. Okay, forgive me, yeah, so this is the commutator. Okay, those green guys are just the rotor coils. Okay, and now here's the new thing. Okay, seeing this coil here, this one and this one, they are just wrapped about this piece of iron here, if you can see it. Okay, and this one is also wrapped around this piece of iron here. Okay, and these are the poles, the north pole and the south pole we've been talking about all the time. So we said these poles that generates the magnetic field inside the machine, they can be a permanent magnet, just giving you north and south, or they can be coils. Okay, and a very small DC machine that can be used in just toys and something like that, they will be just small permanent magnets. But in bigger DC machines, you will see them just like electromagnets like that, to provide more flexibility in the control of magnetic field, like we talked before at the first lectures. And also because in big size machine you will be using a bigger poles, and that means, and actually the permanent magnets is quite expensive. So when you're trying to go up in size of the machines, we usually use electromagnets like this. Okay, so here's the idea. You have a coil just trapped like this and trapped around a piece of iron. Now you have pull, because now it's an electromagnet. It can act like a magnet, okay? And this provides you with a magnetic field going inside the machine, cutting the rotor coils, generated voltage into it. If it is a generator, now this is a generated voltage. Or if it is a motor, it will interact with the other electric current moving inside these coils to create the torque. The whole point now is just these poles, like we have all the time, we just plotted these poles like that. That is north, that's south. But in real life, we don't have poles like this, because the magnetic field want to go from a north to south, and they have to be in a complete path. So these magnetic field lines will try to go back like this, okay? And we talked about this multiple of times, that the magnetic fields likes to pass more through the magnetic materials, the iron or the steel. So even these returning paths, we will not leave it to go in the air like this. And that's mean, rather than having this placed in the air like this, the north and south, no, we will be placing them also around an iron case. So you will put an iron cylinder like this, and now that will be your stator core, stator iron core, okay? Sorry, that was north, not south, yeah. And these are just coils, and you have a coil here, another coil there, and now your flux lines will just go from the north to south like this, and then they travel back in these iron pieces or iron parts to go back to the North Pole, okay? That is much better in terms of the magnetic flux density. The easier you make the path through magnetic flux lines, the more density you get from the magnetic field, and this will be much better for the machine. It will generate you more voltage from a generator, and it will develop more torque for a motor. Okay, guys? If you go back to the video I've been talking to you about, because it will just give us better insight here. This was just the simple machine we're talking about, a north pole, a south pole, and one coil. Now making something more complex, and we use just 2 coils, and now they have 4 pieces of commutator and brushes. Okay, guys? That was the idea we've been talking about right now. Now, making things more complicated and not just having 2 coils, now we have multiple coils, and each one of them are connected to the commutator pieces like this. Okay? These are the coils we're talking about. Placing them, seeing this, now that is the iron core of the rotor. Not placing these coils in the air, because we give the magnetic flux lines a better path to pass through, and these lines like to pass through magnetic materials. So we place this in an iron or a steel core like this. So this iron pieces are what we call the rotor core, okay? And these coils are just placed inside this core like this, okay? And this cylinder we call the shaft, okay? This shaft is basically attached to the rotor. All the rotor and the commutator are attached to this shaft, and this shaft rotates. So everything is rotating here except for the poles, yeah? And the brushes, of course. So your rotor core, your rotor coils, and the shaft, and also these commutator pieces, they're all attached together and they are rotating together, okay? Like you are seeing here. And you have like this brush is being just pressed by this spring to be touching these commutator pieces while it's rotating all the time. Okay, guys? And like I just said, we will not leave these pieces, the black pieces, the north and south pieces from the stator that brings you the magnetic field in the air like that. Rather, we will just place them, like you see in here, in an iron stator core, like that. Okay? So this is the iron stator core. Rather than just having permanent magnets, we are now placing these coils around these poles, and now we have our north and south poles, but coming from an electromagnet rather than just those simple permanent magnets we just used for clarification. And actually they can be permanent magnets, like I said, but permanent magnets tends to be a bit expensive, so We rely on them when talking about small sized machines, but in larger sized machines like the scale we usually talk about, no, we use electromagnets like this. So this is the idea of here. You have two coils. Each one of them will represent you with a pole, okay, like you've seen here, okay, and this provides you with a magnetic field, and this cuts the rotor winding that rotates inside it, and that's how the whole machine works. Okay, guys? So now we understand the whole construction of a whole DC machine in a typical DC machine, and that's actually was our first important thing to pass through. Okay? Before jumping to talk about the next very important thing, I just want to give you an important hint here before moving forward. Okay? So it should be something we talked about before, but I will just introduce two new terminology. They are so important when you're talking about a machine here. Okay? So, like we said, just like any machine has two members. At least, okay, the typical machines we're talking about here, okay? These two members are the stator, okay? And it's a stator because it's basically the stationary part, okay? And a rotor. And it's a rotor because basically that is the rotating part of the machine. Yeah, we know this information. But that's the new part. Just one of these two members, the stator and rotor, we call the field member. Why this field member? That is basically the source of magnetic field. We have said that to get a machine, we need a source of magnetic field, we need a magnetic field, and we need coils crossing this magnetic field, and we need some sort of movement. If it is a generator, this movement is your input. You use an external mechanical source to give movement to the machine. If it is a motor, this movement will be the result of pushing electrical energy to this coil. Okay, guys? So our stator and rotor, one of them will be the field member. It is the source of the magnetic field, okay? In DC machine, like we have said all the time, okay, it is the stator. Okay, so the stator of the DC machine is the field member. So if I'll ask you about a DC machine, I will say, what are the members of this machine? You will say, I have a stator and a rotor, okay? And I ask you which one of those is your field member, you're gonna say this, it is the stator, because in a DC machine, the stator holds the magnetic poles that produce the main magnetic field inside the machine. Okay? And continuing here, okay, the other member we call the armature. And what did this armature are? The armature is the member where the electrical part of the electromechanical energy conversion happens. We said the machine is by definition is an electromechanical energy converter. It's something that converts energy from electrical to mechanical or from mechanical to electrical, yeah? So the armature is basically the member where the electrical part of this energy conversion process happens. And if we talk about it in a DC machine, like we have been talking about all the time, it is the rotor. Why? It's obvious. The rotor winding are those rotor coils that will be cutting the magnetic field, and then the induced voltage will be happening inside them. Okay? So the electric voltage will be induced in the rotor. That's why we call the rotor the armature here. okay? And also be talking about a motor. The rotor winding is these coils where we pushing the electrical energy from outside to be converted into mechanical energy, okay guys? So this idea, we have a stator and a rotor. One of them is the field winding and one of them is the armature, and this will be different from a machine to another, okay? For a DC machine, the field member is the stator. That's the thing that holds your main magnetic poles that give you the magnetic field you need in your energy conversion process. And the rotor is the member that carries the armature winding, where the electrical part of the electromechanical energy process happens. In other types of machines, you will see different things. Sometimes the rotor will be the source of the magnetic field, while the stator will be the armature. This will be the synchronous machine, for example, okay? But it's another type of the machine. The whole point is these are basic principles we have to hold on our mind. The machine has a stator and a rotor. The stator is the stationary part and the rotor is the rotating part. One of them will be the source of the magnetic field, and that is the field member, and one of them will be the place where the electrical part of the energy conversion happens, and this is the armature, okay? So if I am talking about a DC machine and I will call you, I'm talking now about the armature, this will translate it directly in your mind that I'm talking about the rotor. If I'm talking about the field member, this will be translated in your mind directly to be the stator if we're talking about a DC machine. Okay guys? Fine. So all we'll be talking about now about DC machines, we talked about the theory of operation, how the machine works, how the energy conversion process happens, how the generator generates electricity, and how the motor develops a torque, okay? And the second thing, we talked about the construction of the machine, how this machine is constructed, okay? So those 2 points we've been talking about till now, okay? And we'll be doing this with each kind of machine we'll be talking about. We will talking about the construction of the machine, how this machine is constructed, and then we'll be talking about the theory of operation, how this machine works, how the energy conversion process happens. And number 3, all the time we will be talking about the modeling, okay? And that is the basic purpose of the course. The course talking about modeling and control of electric machines and drives. So what I mean by this modeling, okay? The very basic typical modeling way is just using the equivalent circuit model. So I will be talking about equivalent circuit model of DC machine, okay? I will put a square about this model, okay? What I mean by models, okay? The model is something to theoretically represent a physical system. It's not a standard definition, but it's my definition for the model. It is just what if I need to study a certain machine, okay? What if I need to predict its performance? What I need to just know if it is being loaded by this amount of load, will it handle it or not? How much current this motor is taking from the supply, because you will be using this a lot in sizing the other systems attached to the motor, because if you're talking about a motor that will be connected to the supply, that will be need to connect the supply by a wire or cables, and these cables has to be sized based on the amount of current the machine will draw. If you're talking about protection systems that be applied to a motor, because that's an electric appliance and you have to bought some circuit breaker over it, otherwise it may have a short circuit and give you a problem with the system. So this circuit breaker also is being sized upon the amount of current the motor will draw, and etc, etc. The whole point is you need to have some sort of representation of this physical machine we've been talking about. So the machine is this physical system. It's just wires, winding, iron, steel, commutator brushes, other stuff. So if I'm ask you how much the current this motor, if it's working as a motor, will draw from the supply, you will just take it and go to the lab and attach it to the supply and use an ammeter to measure the current going from it. But you will not be able to do this in all your industrial facilities working about. We cannot just trial and error with everything, because rather than this, if you just go with this approach, we actually may damage several machines just to know how many current it will draw or how much load it can handle. So the whole point is we need to model this in a theoretical way, mathematically. That's what I'm talking about. We need some sort of set of equations to use to predict the performance of this machine. Not any machine, but a particular machine. Okay? So if you have a machine in your hand, and me as a manufacturer of this machine gives you some information about this specific machine, you can use a set of equations or a certain theoretical model to predict the performance of this machine. Okay, so if I'm talking about this equivalent circuit model directly, I will be saying this is mean using an electric circuit, and by solving it just like any kind of electric circuit you used in whole your life, okay, we can predict the performance of a specific machine. And that's awesome. Okay, now your real machine is safe. You will not conducting direct experiments over it, or unguided experiments, let me say that, because that's the whole point. I'm giving you a motor and I'm saying just let me know if this motor will just use with an elevator system, how many people will be in this elevator and this motor can just lift them. Okay, you can just take this motor, attach it to the elevator, and now just give 10 persons go on the elevator and I'll let the motor carry them, because maybe those 10 persons will be so much for the motor and the motor will be burned out, because you just need to test it like that. So we won't do this. We will just use a model like this equivalent circuit model we'll be talking about, and we have some information about the machine from the manufacturer of it, and plug this information into this model and predict if this machine will handle this load or not. Simple as this. Okay guys, so let's play. So I have in this machine two members. I will be modeling them now separately. Okay, so the first one is the armature. Okay, in a DC machine the armature is the rotor. Do not forget this. Okay, so the armature, basically here we're talking about a set of coils, like we said before, in the rotor of this machine. Okay, so if I'm talking about the machine as a generator here, or a motor, each conductor has induced voltage of E equals BLV. If you remember, this equation we'll be talking about a lot. Okay, knowing that this V is your linear speed or velocity measured by meters in seconds. Okay, but actually we don't like this linear velocity, so I will just say that's V equals omega m multiplied by R. Okay, this equation is known from your mechanical courses, where omega m is the mechanical angular speed in radians per second. Okay, and R is basically the rotor radius in meters. Okay, so this is how to convert from V, which is the linear speed, to omega m, which is the rotational speed, mechanical angular speed. That's what I'm saying about, and that's the thing we like most. Okay, so substituting this, so E, sorry, of just one conductor here. Don't just, yeah, I will call this E conductor. Okay, will equal B L omega M multiplied by R. Okay, guys? If you remember this, it will look like something like this. This E conductor will be something like this. Remember, using the commutator, it will be just look like that. Okay, and you'll have a zero period. We have just reduced this much using more coils, but it will not be exactly zero, because to make it exactly zero, that means you'll need these coils just to be attached to each other, just connected to each other like this, and it will not be like that. Okay, so this B we're talking about here, or this idea is we will talking about the average value. So we are looking for this average value because we're talking about a DC system. Yeah. So this E average bare conductor will equal the B average, because it's coming from the flux density. If the flux density is just continuous like this, DC, this will give you the idea, L omega M R. Okay, remember I'm talking here about just one conductor, and we did nothing, just so this equation E equals B L V we've been talking about a lot before. Now we just taken this V, the linear speed, and substituting by the angular speed omega mr, because we like to talk about how many rotations per second and that stuff. That's much better than talking about linear velocity. And now I'm just taking the average value for it. Okay, how to calculate this B average value? So this B average value, the average value of the flux density, okay, that is the idea how to calculate this. So that is the flux density in Tesla, and this equals phi over A of a pool. What is this? Phi is the magnetic flux itself, measured in Webers, and A pool is the cross-sectional area of a pool. Okay, you remember these poles, the North Pole and South Pole, been talking about all the time. So to calculate the magnetic flux density, by definition, the density is this amount, the magnetic field, divided by the cross-sectional area. Okay, and this flux is coming from a pole, so you just divide this flux by the cross-sectional area of the pole, and this will give you the flux density, B average. Okay, so doing the same idea now, how to calculate this cross-sectional area of the pool, A pool. Easy. You're talking about a cylinder. That's the stator is a cylinder, like we said before. The rotor is a cylinder and the stator is a cylinder. Yeah, so that is the side area of the cylinder, 2 by RL and divided by P. What are these 2 pi RL? The side area of the stator. Why this? Because it's a cylindrical shape. It's a cylinder. Okay, that is the side area of a cylinder. Okay, guys, remember these 2D. That is the whole point here. Okay, so that is here is just an internal cylinder like this. Okay, if you look at the 3D, we're talking about just a cylinder like that. So that's a cylinder. Okay, and we don't talk about here just 2 pools like this. Usually it's just more than 2 pools. Okay, so you'll have another pools like this here, another one here, and another one there. Okay, and this pool area, it will be just this cylinder area, the stator cylinder area, okay, divided by these number of pools will just give you how much of an area each pole of them is taken from this stator cylinder. Okay, so how to calculate this? It's just like this. It's 2 by RL. Okay, guys? What is this L? It is the length of the machine. Okay, the length of the cylinder. So back to this. This will be the length of the cylinder, the depth of the machine. So call it L, the length of the machine, or call it the depth of the machine, whatever you want to call it. Okay, so now we are just calculating the side area of a cylinder like this. Okay, so it's 2 by R, which is the radius, multiplied by L, which is the length or the depth of this machine. What is P is basically the number of poles. So whatever the number of poles is, you're now getting the share of this pole in the total side area of the stator cylinder. Okay, guys, that's the idea. The stator is your source of magnetic field. You get the side area of the whole stator and divided by the number of poles. Now you get the cross-sectional area of a single pole, and you divide the total flux by this value, and you get the average flux density or volt. Okay, guys, so easily now E average equals phi over A pole, which is B, multiplied by L omega mr, which is V. Okay, guys, so I have substituted by A pole, which is 2 by RL divided by P, and just do the math. It will give you P over 2 by phi omega m. And remember, that's bare one conductor. Okay, what if I want to make this for the whole armature? That will be E average for the whole armature. So you basically will multiply this by Z. What is Z? Z here is just the number of conductors in the whole armature. Like I said before, you just calculate for a single conductor from Faraday's law, E equals BLV, and just multiply by number of conductors. I will give you the whole induced voltage in the armature winding. Okay, guys, knowing this from here, all these values, Z number of conductors is constant, P the number of poles is constant, nothing there changes while the machine is working, you know, divided by 2 pi, which is basically a constant. So this whole is just a constant. We'll call it K. And it will give you this very well-known equation, just EA, the induced voltage A in the armature, equals K phi omega m. And that's measured in volts. It's a very, very important equation. Now we can quantify the amount of energy, or the amount of electric voltage induced in the whole armature of the machine, like we said before. If you know the constant K, which will denote by number of conductors, you can get this from the manufacturer of the machine. Number of poles, you can get this from the manufacturer of the machine. Okay, and divided by 2 pi. Now, if you know the speed of rotation, you will be rotating the machine, omega m, and the amount of magnetic field inside the machine. Now you can calculate the induced voltage in the whole armature like this. Okay, phi is the magnetic flux and omega m is the speed. And now comes again this to give you the whole principle of generation. To get an electricity generated by a machine, you need a speed of rotation of these coils inside the magnetic field phi. You need a speed omega and a phi magnetic field, and those together will give you induced voltage A, armature, EMF, electromagnetic field, so EMF, induced force, the electric voltage. That's what I'm saying. Okay. So the voltage in volts is K constant multiplied by phi multiplied by omega. Okay, guys? So this, what you do in just quantifying the EMF in the armature, okay? And now you can use this just to calculate the amount of voltage generated by a DC generator, okay? What about quantifying the torque? If you're talking about a motor, okay, like we said before, that will be the same idea. The average torque is basically RLB average I. Remember this equation? BLIR, the torque coming from a single conductor. So, and it is the same idea that this torque will be like this, and we will be just looking for the average value of it, T average. So you get it from the average value of the flux density. It is the same equation of the flux density like before, phi divided by A pole, and the A pole is 2 by RL divided by P. Okay, if you put the same thing here, it will give you the same thing. The torque of the whole armature equals the same constant K multiplied by phi multiplied by I armature. This TA is the armature torque, the total armature torque in Newton meters. The K is the same constant we talked about before. Phi is the magnetic flux, and IA is the armature current in amperes, and this flux in Webers. Yeah, this torque value is in Newton meters. Okay, guys, and again, that is the total armature torque. So the same idea. A torque comes from a combination of a magnetic field coming from the field member, from the stator poles, and an electric current moving in the armature coils, IA. Seeing this from the equation? So that's the basic idea I talked about. We talked about the modeling. The modeling is how to mathematically, theoretically represent this physical system. Okay, and these equations actually reveals this connection. We said to get a generation, you need a rotation inside a magnetic field. Here's the equation. The electric voltage induced coming from multiplying phi by omega, which is the flux, by the speed. And the same idea comes about the torque. To get a torque developed, you need a conductor carrying electric current moving through a magnetic field. And that is the equation give you this. It is just you need a magnetic field and you need electric current moving inside a conductor that is involved in the constant K, because K will equal ZP divided by 2 pi. That is K. Sorry. K equals ZP over 2 pi. Okay, guys? So here's the 3 components we talked about a lot. A generator needs 3 components to be conducted. A conductor moving by speed through a magnetic field. Here is the equation, K phi omega m. K has the number of conductors, and phi the magnetic field, and omega m is the speed. The same idea here, we're talking about a torque. A torque means a conductor carries current inside a magnetic field. Okay, so here's a conductor, the constant K, which holds the number of conductors Z, multiplied by current inside a magnetic field phi. Okay, guys? That is the whole point here. Okay? So these equations can be represented directly using this. So now I'm talking about modeling. Okay? To model the armature of the machine, so the armature is basically just winding, set of coils. Okay, guys? So if you want to model them, you will be modeling them like you model a coil. like in electric circuits. It will be looking like this. Here is the voltage applied from the terminal. Vt is the terminal voltage. And this resistor is Ra, the armature resistance. And this is Ea, a voltage source representing the induced voltage inside the armature, like we just investigated. There is the internal induced voltage. Okay, guys? And this will be Ia, the current of the armature. Actually, it can be going out like this or going in like this. What is the difference? Easy. Ia will be out of the machine in case of a generator, because that's the basic idea. The generator, the machine that generates electricity. Okay, so the current is moving out of the machine to the terminals and going out to the outside world. Ia is going inside the machine like this, inside, or going to the machine, going inside the machine if you are talking about a motor, because the motor needs electric energy. The motor converts electric energy into mechanical energy, so the current has to move from the source to the motor. So here's the whole point, guys. This induced voltage Ea is the value we've been just trying to quantify here. That is Ea. Okay? And that's something inside the machine. But if you're talking about a generator, this value is not the voltage that you will just appear at the terminals of the machine, because these coils are still having internal resistance, Ra. So you will lose some of this voltage as voltage drop over this resistor if you're talking about a generator like this and the current is moving from inside the machine to the outside. Okay? The same like if you're talking about a motor. The voltage coming from outside the machine connected to the terminals of the machine will not be transmitted directly at all inside the machine, because again you need to lose some of it as voltage drop over the resistance of the winding, because those winding, these coils you're talking about, they are not ideal, they have a resistance. Okay, so the induced voltage inside the machine does not equal the terminal voltage, because there is some resistance in the coils, like we did before in just your equivalent circuits, or just in your circuit courses and all that stuff. They're all having this. If you're talking about a coil or anything that's been modeled, it will have some internal resistance to represent. Okay, guys? And while these just black pieces, they are your brushes. Okay? So it means like this is just, these brushes will be just plotted like this to just remind you this Ea is an internal voltage inside the machine, and it will not be directly the terminal voltage you will get outside of the machine if you're talking about a generator or even a motor. Okay, guys? So I'll be talking more next time about these modeling criteria, how to just actually have this electric circuit modeling. But this is the basic idea to get in your mind right now, is just you will be having an induced voltage inside the machine like this, can be calculated like K phi omega m, and K equals ZP over 2 pi, and we just derived these equations together today. And if you know the resistors, the armature resistance of these coils, and you can basically find this easily from a manufacturer's catalog, or even you can just measure them like an ohm meter or something, and you will be finding this armature resistance of the machine. And now you can simply use a simple circuit like this to predict the current that can be just moving inside the winding. It's easy. If you can calculate EA from the equations we did before, and you will absolutely know the terminal voltage because it's something measurable. You know the source that will be connected to the machine. Now you know everything in this circuit, and you can just solve it directly to find IA. Okay, IA from now will be EA minus V terminal divided by RA. That's for a generator. Okay, or will be equaling V terminal minus EA over RA. That's for a motor. Okay guys, because that's basically, if you're talking about a generator, that means the internal voltage is higher than the terminal voltage because the voltage inside the machine will be big to push the current out of the machine, because that's a generator and the current goes out for the machine. If it is a motor, that means the terminal voltage will be higher than the internal voltage, otherwise the machine just because the current will just be moving from the supply into the machine. Okay, we'll be talking about this again, don't worry about this. So that's the thing I need you to go out with. That is an electric circuit that's represented your armature. Okay, so if you can calculate the internal induced EMF E armature using this equation, and you know the terminal voltage, and you know the armature resistance from the catalog of the manufacturer, or be measured using an ohm meter or something, now you know all the information and you can calculate the amount of current. Remember that we told you we need to model the machine to know how much current it can take from the supply if it is a motor, or gift supply if it is a generator, or all that stuff. Now we can do this without having the actual machine and just attaching an ammeter to it to see how much current it will draw. That's what I mean by modeling, mathematical modeling of the machine. Now we have a simple electric circuit that represents the actual machine and can tell you how much current will be passing through the winding of the actual machine without having to test the actual machine directly. That is the whole point of this modeling approach. Okay guys, so next time I will be stressing on this again to make sure you understand what's happening directly, and we'll be talking about how also to model the field winding, because all this will be talking about just the armature winding. It will be something like this, how to model the field winding, and now we'll be having a full model of the machine, and we can use it to predict the whole performance of this machine without just having an actual machine tested to just predict its performance. Okay guys, so take time to review this, and I will be happy to get your questions on Friday morning if you have any. Okay, thank you so much for joining me today, and I will be seeing you next time.